Tangents and radii are perpendicular. A tangent and radius drawn to the point of tangency are perpendicular. Given circle O and line ABC where B is a point of tangency, prove that OB is perpendicular to line ABC. Let's use an indirect proof. Either the line through O is perpendicular to line ABC at B or it's not. Let's assume it's not. Now we assume there's a point D on line ABC where OD is perpendicular to ABC. This makes triangle OBD a right triangle with right angle at D. The longest side of a right triangle is the hypotenuse, which is opposite the right angle. This means OB is greater than OD, but it's not. The point D lies outside the circle, so its distance to the center is greater than the length of the radius. So we have a contradiction. Our assumption is incorrect. Therefore, the line through O is perpendicular to line ABC at B is a true statement. Auxiliary lines and labels. In problem solving, understanding that tangents are perpendicular to the radius drawn to the point of tangency is a big deal. If the radius is not shown, the line postulate gives you justification to draw one. So do it. There might be value in drawing segments to create right triangles too. It is the line postulate that gives you freedom to draw auxiliary lines to help in problem solving, like this line here from O to C. Given circle O and ray CB, where B is a point of tangency, BC equals 20 and DC equals 10, find the radius of circle O. Step 1, draw the radius. Step 2, identify the right angle and the right triangle. Step 3, label the radii with the letter R. Step 4, solve using the Pythagorean theorem. So we have r squared plus 20 squared equals r plus 10 squared. Here we have the answer. So 20 squared becomes 400. This becomes this trinomial. All right, solve for r, and we get r equals 15. So that's the radius. Theorem. Tangent segments from a common external point are congruent. Given circle P with RA and TA tangent at R and T, prove that RA equals TA. So we begin with our given information, then we draw PR, so this line here, we draw PT, this line here, and we draw PA, this line here, because of the line postulate. We know that PR is congruent to PT because all radii are congruent. Segment PA is congruent to itself because of the reflexive property of congruence. We know that angle PRA and angle PTA are both right angles because at a point of tangency, the radius drawn to that point is perpendicular to the tangent line. We've shown that PR is congruent to PT and PA is congruent to itself, and we've also shown that both of these triangles are right triangles. Therefore, they are congruent to each other because of hypotenuse-leg triangle congruence. Since we have shown that these two triangles are congruent to one another, we know that this side is congruent to this side because corresponding parts of congruent triangles are congruent. And here is the full proof of the theorem. Given that RS and RT are tangent to circle C at S and T respectively, the value of X, that's what we want to find. So we know that these lengths are equal, so we can just set those equal to each other. 3x plus 4 equals 28, so 3x equals 24, x equals 8.